In this video, I'm going to show you how to find the step response of a control system. Let's still use the example we discussed in the class about the vehicle cruise control. Let me explain this code to you line by line. First, it has some comment. The comments are used for you to show the purpose of this code. You can write down the author and corresponding figures in the book. For example, the figures in your homework. In line 6, it clears some variables. When I run this code, you see in the workspace, some variables have been generated. So when you run this program again, we do not want to have the old variables. Then we can use this command to clear all the variables. So if I paste the command here and hit enter to run it, you see all the variables has been cleared in the workspace. Close all, it will close all open windows. CLF means close figures. Hold off, it means when we use the command plot to generate figures, then two plots will not draw on the same figure. Then we can define some variables. So M is the mass of the vehicle. The unit is kilogram. So M is 1,000 kilogram. So B is a viscous drag coefficient. B is 50. U is engine force. Its value is 500. Its unit is Newton. Now we can use this command. S is equal to TFS. The S is a complex number. It is the S in the Laplace transform. If you still remember the transfer function in the vehicle cruise control is a system. We call it the model. Then the transfer function is Vs over Us. So V is the velocity, U is the engine force, 500. We have the transfer function 1 over M. Denominator is S plus B over M. We would like to study the step response for this system. We can use the command step for unit step response. But here, US is a step signal. It is 0 when t is negative. When t is greater than 0, it is 500. Since it is not a unit step, its step size is 500. So when we call the command step, we need to time the step size. So we have the system is a trans function, then times the step size is 500. The second argument is the T final, is simulation time. We simulate the step response from T is equal to 0 until the final time of T. Here, the final time is 100. It means 100 seconds. We know the control is all about dynamics. We care about the dynamics. Therefore, the output of step response generates two variables. The first variable is the output, the velocity. We use y. Then the second output is the time. Then we can plot the time and the velocity. It shows the velocity for every second from 0 to 100 seconds. The constant 2.237 is used to transform the unit of y, that's the speed, from meter per second to mile per hour. If we use the standard unit, then the output of the velocity will be meter per second. Since in the United States, we usually use mile per hour as the unit of velocity. So we time 2.237 to transform the unit of the velocity to mile per hour. Then we can assign X label is a time, the unit is second. So Y label, the velocity, its unit is mile per hour. To run this program, we can click on Run in MATLAB. It will generate this figure. In this figure, it starts with 0 velocity at time 0. It shows the velocity for every second. For example, here, if a 500 Newton engine force is applied to this vehicle in 2 seconds, its velocity is 2.129 miles per hour. Then in half seconds, its velocity is about 17 miles per hour. In a minute, its velocity is about 21 miles per hour. And in 100 seconds, it will be over 22 miles per hour. It shows the velocity for every second when a 500 Newton engine force is applied to the vehicle.